Okay. Thanks for. Oh, sorry, it's not. It's getting. Hello, everybody, and thanks for introduction, and thanks for organizers, for giving this opportunity to talk about our recent work on the cooling. Today, I'm gonna talk about the role of the different resources in the cooling, the quantum system. This talk is based on the two project we have done, and then one of them is the new, it's from the last month. Yeah. Yeah. As you know, when we want to do any quantum information test or quantum computation, we need to have the pure state, and the pure state is not is not free, and then we need to do the operation to have the pure state. But the question is, what is the cost of having the pure state in general? And then when we want to cool, and which type of the resource play the role? For example, when you are cooling and then you are doing the operation, okay, you need the time and you need the money, of course, and you need the energy, and also you need to have the control on these systems to properly do the process you want. And then in this way, you can cool the system for doing the task. But in general, from the thermodynamic perspective, we want to know what is the main resources, and then how we can answer this question. To answer this question, we can maybe we can use these two principles. The first one, the statement from Landau says information is physical, and then when you want to erase the information or pure the state is they are equivalent, then you need to spend at least kT log D for qubit system energy, for kT log D energy for the unit of energy for qubit systems. And then most of them is more than this. And then it tells, okay, based on this, then you can cool to ground state and with the finite energy. But from the other side, we have Nair's unattainability principle, and that is the third law of thermodynamics. It says with the finite resource, we are not able to cool the system to the ground state. And it seems there is a contradiction, but actually there is no contradiction, because if you look at the Landau principle with more details, then you can see, okay, if you want to reach this amount of heat dissipation, you need to have infinite time, and then you need to do the process very slowly and then infinite time. It means in your case, time can be the resources, or you can do in the finite number of time steps. But there you need to have the infinite control complexity. You need to deal with the very complicated system, very big system, and with the long-range interaction. And then in this case, of course, in the last one, you can cool to ground state, and then time and energy is finite, but you have another resource which we call control complexity, and this should be the infinite. Okay, then so far we have three different resources: time, energy, and control complexity, and we want to see what is the relation between them when we are looking for the cooling process. And to do this, we need to have this framework and to see what is the relation between them. And then for this, we need to have something there we can, track all the resources. And because of this, then we will focus on the two framework. One is the coherent one, and another one is incoherent one. In the coherent scenario, what we have is, this is the collision model, normal collision model people are using, is we have our system and the system is interacting with the machine. And then at each step, you can bring the new machine, and then you can use the unitary interaction to do this process. And here we are assuming a system and the machine initially starting from thermal state, because we are assuming thermal state is free, and then we are allowed to do the arbitrary unitary. And also, since we are doing the arbitrary unitary, then it means there is another external agent. It's kind of doing the work on your systems. And in such a scenario, then if we look at these three resources, and then, for example, if we want to see how we can reach the pure state, then if for the first one, energy one, if we have a system and then another qubit with the gap infinite, then this qubit is kind of the machine qubit is like the pure state. And then if we do the swap, then we can have the pure state. But the cost of having this, if you look at the energy cost and then the energy exchange of the machine, then you can see, since the gap is infinite, then you need infinite energy. Then, okay, you can have with the infinite energy, but yeah, you just need to use the infinite gap to do this process. For the second one, for investigation of the control and the time, we can use this Landau revolve equality for Landau, and then the cost, and then there they showed, for when system is interacting with the thermal state, then the energy exchange of the machine, when system is interacting with the machine with the thermal state, the energy exchange of the machine, it depends on the entropy exchange of the system plus two positive terms. One is related to the amount of the correlation you can create, and another one is the difference between the state, initial and final state of the machine. Both are positive. And then in this way, then you can say, in any case, for any process, then the energy exchange of the machine would be larger than delta S. And then Landau, this is equivalent to the Landau principle. It's like the minimum amount is the delta S. And yeah. But if you want to reach the minimum one, then you need to have the infinite resources. And then, for example, you can use the infinite time, and you can do with the infinite time, like in this way, using the collision model, where you have, here we are using the qubit system, but you can easily extend to the qubit one as well. And then you have a qubit system, and then what you need to have the n qubit as a machine, where the energy gap of this machine is slowly increasing, and then you just need to do the swap at each step. And by doing this, and then if n goes to infinity and delta goes to 0, then you can reach the Landau cost. And then with the you see, since your system is at each step interacting with the one machine, then you just have finite control, but the time is infinite. But instead of this, what you can do, you can have the collective unitary. It's like the multiplication of all the unitary you are using, and then you have very complicated unitary, and then but if you want to generate this type of the unitary, then you need M-partite interaction, and it's very complicated. And then you can do the similar things, and you can reach the same energy cost, and then you can reach the Landau cost. And also, since you are using the one unitary, then time is one, and then you are doing the finite time. But in this case, the complexity is infinite. But in both cases, then you can have the Landau cost. But what is the complexity in general, and which parameter play the role? And for this, we have two different notions of the complexity, and one is the structural complexity, and which is related to the Hamiltonian structure, dimension of the system, and the energy spectrum of the Hamiltonian. And another one is the control complexity, and then it is related how fine-tuned control we are using to unlock the machine potential in general. And then we need to have the order, and then we need to have the perfect control on that to do this. And then if, for example, here you can see some parameters of the, the play the role in the cooling. For example, the maximum energy gap of the machine play the role, and then it's kind of tells you how much you can cool the system. Or if you want to look at the energy cost, again, then you can see here, you have Landau cost plus some term is related to the dimension, and by increasing the dimension, this term would vanish. And but for the control complexity, so far we don't have a general definition, but what we can do, for example, here we are using the basic notion, and then it's related to the rank of the non-trivial part of the unitary. And then we saw, if, for example, in the previous case, this rank goes to infinity to reach the Landau cost. Okay, so far we talked about the coherent one, but now we can talk about the incoherent scenario. In the incoherent scenario, okay, again, we are using the collision model, but in the collision model, what we have, our system, instead of interacting with the one machine, interacting with two machines with two different temperatures. One we call hot machine, and another one is the cold machine. But here we are just applying the energy conserving unitary, and there is no external agent, and then we just need to turn on off this process. And then the hot part play the the agent role, and then it's kind of the energy supplier for this scenario. And in this case, we can show with the infinite energy, it's impossible to cool the system to the pure state. But again, similar to the coherent scenario and the revolve equality, we derived this with this equality based on the free energy exchange, and the energy exchange of the hot part, and the other part is kind of, if you look at the right hand side, you have positive terms, and because it's related to the local entropy change and the relative entropy. And there you can see you have eta. Eta here is the Carnot efficiency, and then if based on this equality, you can show it's impossible to cool the system to the ground state with the Landau cost. And this, of course, in one special case you can do this, and this is related to the case when eta is equal to 1. Eta equal to 1 is equivalent to have the thermal state with infinite temperature. In this case, you can cool the system to ground state, but the problem is when the temperature of the hot machine is infinite, then it takes infinite time as well to go there. In a similar way, you can find, okay, since the right-hand side is negative, then you can write this, you can find this inequality, and the optimal one is given when this inequality reduced to equality. And then if you want to reduce the equality, then you need infinite time, or you need infinite control. And then you can reach this equality relation. But in both cases, you need to have the infinite structural complexity. Infinite structural complexity, in any case, is necessary for doing this process. And but so far, okay, we looked at the asymptotic case, and then we saw the role of each of these terms in asymptotic case. Now we want to focus on the the finite cases, and then we saw that this asymptotic the infinite structural complexity is necessary for cooling to ground state, but with the finite energy. But now we want to focus on the finite structural complexity. In this first, we will focus on the coherent scenario. In the coherent scenario, what we have our system, and then we are allowed to choose. We have also the n machine, finite but enough large a machine, and then but we are allowed to choose the Hamiltonian structure of this machine to reduce the energy cost. And then what is the task? We want to cool from some thermal state with temperature T with some another thermal state with the colder temperatures, like with inverse temperature lambda beta. And then in this case, if we had the asymptotic, if we have infinite energy gap structure, then we just had this Landau cost. You can reach this one. Heat dissipation is just related to the entropy. But here, because of the finite resource cases, then we have extra term, and this is like the correction term. And then this correction term is you see there is L star, and thanks to thermodynamic geometric approach, then by using the thermodynamic lengths, you can analytically find this one L star, and then this equation, and then you can see it's just related to the initial and final state. And yeah, but if you look at this scenario, what we are doing here, we did, yeah.
I think we are kind of running out of time. I mean, if you can try to summarize in a couple of a minute or two.
Yeah. Just this is kind of the last slide. Yeah. And then you can do similar thing with the incoherent scenario. And the incoherent scenario also, you can find the correction terms. And the correction terms, again, is related to this minimal thermodynamic lengths. But for the qubit system, also you can see you can optimize on both unitary and the Hamiltonian structure, and then in both cases also is given with these two equations we show here. Okay, maybe I can skip the outlook.